The quantum liquid, certainly there's many definitions. More Euro definition of quantum liquid is a phase that without a shape.
Without
shape, it can do not resist shear deformation. Is liquid, yeah. There's another sense of quantum liquid is that it's a state which you can dissolve product states. You can enlarge the system by adding product state. The Fermi liquid is not like that.
You cannot add the product state.
Yeah, you can add product to enlarge system, but when you're using the local unitary to get the equivalent states, the Fermi surface actually shrink. Will shrink. Yeah, we add because product states cannot contribute to Fermi surface. It's a product is more like a gapped subsector. And yeah, the reason is following. No, okay, let me just say the low energy effective theory from liquid have many fields. The number of fields equal to linear size of system. So when you increase system size, you should increase the gapless field. Number of gapless field has to be increased. But adding product state do not increase number of gapless field. So this is a reason why the Fermi liquid is not liquid in this sense. Yeah, the quantum Hall is a liquid. This Dirac Fermi point is a liquid. But yeah, with the area law in entanglement is like liquid. Yeah, but the Fermi liquid is not area law, so that's also related. Yeah, so it's really reflect that we understand entanglement better. So entanglement reveal some structure we didn't appreciate before.
Fermi liquid has no entanglement.
Have entanglement because of Fermi surface. There's a lot of entanglement, and they have very special structure, which make it not a liquid. Yeah, the entanglement structure in the Fermi liquid is kind of special. Yeah. We should start. Okay, so let's start. So yesterday, we basically describe or define or maybe characterize this topological order using a quantum information point of view. Yeah, either using entanglement, whether the system is shortly entangled, longer entangled, etc. Okay. And but our discussion is very abstract. Just we cannot do this, or we can do that, And today we try to maybe get some more concrete example. So what do you mean by long-range entangled? What is the example of a long-range entangled states? So certainly, like this, some pattern for up or down, a single state is a product state, so it's not long-range entangled. Okay. And then this, so all the spin pointing in the x direction, also like non-entangled. Then we may say it's a superposition of product states, this up and down, may be entangled. But however, if you do the equal weight superposition of all spin configuration, then it's actually the same as this spin in x direction, so it's not entangled. Okay, so this gives us idea. If you do superposition, we should do that properly, not too much. If you do too much, we get nothing. So we sum over a subset of spin configuration. That's a key point. So there's a lot of game to play. Which subset? You can design the model, design interaction, so that the ground state is superposition of some subset. Okay. So one way to do the subset is to include interaction such that spin down state want to form a string, closed loops. You can imagine there's some interaction term which favor this spin down state, which form a loop without end. The string end costs energy, but if no string end, it don't cost energy. And then you also include interaction where the string can fluctuate without breaking up. So this way we get a superposition of strings which are formed by down spins. Okay. So therefore this that is one of a spin wave function, which we think is a long range entangled. That means there is no local unitary transformation which can transform such a wave function into the product states. Why? We'll see why is that. We can play some games. Maybe here is an equal weight superposition. We can have a plus or minus superposition, where the sign depends on whether the number of loops is even or odd. And then we can also put some phase factor. Actually, one may say, this kind of superposition too artificial. What's interaction give you a string? Looks like you need a complicated interaction. But however, this kind of wave function is not so ridiculous. We know that in the anti-ferromagnetic states, the spin want to form a singlet. So here is like in Coulomb lattice, for example, and this dimer is a spin singlet. But the spin singlet may fluctuate. These are RED states. And so maybe that's one configuration, this is another configuration. Okay. Then if we compare these two configurations, just lay one on top of the other. So we think the red is reference. Then the blue is a fluctuation of a red. And then compare red with blue, which I lay these two configurations together on top of each other. Then suddenly you see that red and the blue form a string. This here they form a string. And we have this an unpaired spin. Unpaired spin is the end of string. You may say, oh, here they also have two ends, but actually this is a small loop. This go from here to here, then back. So this is a small loop. It's not end. This one is really a end of a loop. So therefore, this dimer fluctuation is described by strings. So dimer fluctuation and string fluctuation are the same. So actually, this kind of dimer fluctuation is a good approximation of this string liquid. Not exactly, but a pretty good approximation of that. So this kind of string liquid is pretty realistic, So usually that's typically people. I think you heard a lot of people say we are looking for spin liquid, which may have an interesting thing, because a spin liquid is in some sense very much like a string liquid, and the string liquid have long entanglement, topological, all that. So this is kind of motivation for looking for spin liquid. Okay. And so now let's consider some Hamiltonian which realize a string liquid. Okay. And the point is that we have local rules, because the string, so the spin fluctuating or string fluctuating according to some local rules. One rule is that this downspin form a loop with no end. We can imagine we can have a Hamiltonian, local Hamiltonian to enforce such a condition, open end with the cost energy. Then another thing is that we have a local Hamiltonian which break this string up, break up the string and reconnect them this way. So basically, from this kind of connection, from horizontal connection to vertical connection. So we can imagine there's some local Hamiltonian term flipping spin in a certain way and making that can change. Okay. And so basically these two dancing rules is that another dancing rule is that we can add a little small loop, add a loop here and deform the loop. That's also local Hamiltonian. So we'll design Hamiltonian this way, enforcing these local dancing rules. And then you will get a global dancing pattern, which is a superposition of all loops. Yeah, that's just kind of cartoon way to explain what Hamiltonian should do. And then for the second string liquid with plus minus sign, we just need to change the sign of this term. When the Hamiltonian, which is flipping, reconnect the strings, if you're changing sign of that term, you may add the minus sign here. Ground state wave function, then that's give you this a different wave function. Then I want to emphasize that the first wave function works in 2 dimension and 3 dimension. However, the second wave function works in 2 dimension, but not in 3 dimension. The third wave function actually do not work in both 2 and 3 dimension. The reason is that like a second wave function, reconnection with the changing sign. This kind of fluctuation is so-called, there's no frustration in the sense that you can see when you will reconnect this, if you look at the picture, the number of strings changed by 1, either increase by 1 or decrease by 1, but doesn't matter. In either case, we can change the sign. So therefore, you can apply this reconnection many times, but you get a consistent solution. Whenever you have every reconnection is changing from even to odd to even, but the even have positive sign, odd have negative sign, which are really compatible with this kind of sign change. However, if it is a phase, it doesn't matter, do not compatible, because this kind of reconnection sometimes increase, sometimes decrease, and then we have now the phase factor increase, decrease give you different same results, or maybe the different results. Then things get confused. And also in a 3 dimension, we could have this kind of overcrossing. In this case, reconnection do not change in number of loops. So this rule actually become frustrating and don't work. So kind of interesting that there's a certain dancing rule, depending on dimensionality. Actually, that reflects certain entanglement that appear in 2 dimension, but do not appear in 3 dimension. Yeah. And it turns out that this kind of entanglement have emergent fermion. Emergent fermion is okay to exist in 3 dimension. And this kind of entanglement have emergent semion. Semion cannot exist in 3 dimension. So that's why this wave function is inconsistent in 3 dimensions. So everything kind of fit. So that's just cartoon picture. So now that's the main thing for today is that actually there's a way to have a concrete Hamiltonian to realize that. And so the concrete Hamiltonian actually is pretty simple. We have a spin live on the link. Say I'm choosing the honeycomb lattice, the link of honeycomb lattice. Then we have a Q term. This Q term is a product of Z operator around each vertex. You can see for each vertex, there's 3 links attached to it. So there's a 3 Z operator multiplied together. So this is a product 3Z. So what this operator do is following, because the Hamiltonian have this UQ, U is big. With minus sign, that means the Hamiltonian say that the Q must be equal to 1 for the ground state. Okay. The Q equal to 1, that means this Z, 3Z should have a 2 spin up or no spin up. Yeah. And sorry, 2 spin down or no spin down. Spin down is a minus. So when you have a no spin down, so like here, the black dot is spin up, no string. Spin down means a string. So that's here there's no string. And we have 2 spin downs like this. Yeah, you have a string on the 2 link which goes through this vertex. So you can see this term enforcing this constraint that on every vertex, either you must have incoming string and outgoing string or no string. We cannot have a single incoming string, no outgoing. Then that's string and the cost energy. So this term enforcing the closed loop condition. And this F term is defined on the plaquette. So this F term is a product of 6 X operator around the plaquette. So just flip spin around plaquette, that's adding a thermal loop or deforming a string. So this is like a string hopping. This is a string constraint, and this is a string hopping, makes string fluctuate. And when you have this both term, the ground state, this Hamiltonian is a string liquid. And this Hamiltonian is exact soluble because this Q term, F term commute with each other. And so it's a commuting projector model or stabilizer code model, also is exact soluble. The ground state basically is an eigenstate for both this local F operator and local Q operator. And so the eigenvalue of this operator just equal to plus minus 1. So ground state means that it's F and Q both equal to 1 on every site on every link. Yeah. So that is a irresolvable wave function. Okay. And so from here, we actually can show that the ground state have fourfold degeneracy on the torus. Yeah. Because on the torus, we have 4 sectors. And the string can wrap around whole torus in horizontally or vertically. So there's 4 sectors. And for this 4 sector, just for the 4 sector, this both F and Q have eigenvalue 1, and so they have degenerate energy. Yeah, that's it. Yeah.
So in the previous page, what's the difference with the k-type torical? This is just k-type torical.
Yeah, it's k-type. It's just on the horizontal lattice. Actually, torical can be defined on any lattice.
So what do you want to say? It's just a reinterpretation, or this can be derived from string net.
Yeah, no, it's say that this is a cartoon picture to say we have a ground state have this kind of string liquid ground state. I just give you a concrete Hamiltonian. The ground state, this concrete Hamiltonian is a string liquid. Yeah, that's a point.
Reinterpretation, any you
it don't have any interpretation. It's just here I just say this string liquid is a potentially may have a topological order, have long-range entanglement. And then the question is that can you give me a concrete Hamiltonian whose ground state are indeed a string liquid, whether it's realizable? Because here I just write down the wave function. You can write down the arbitrary wave function. But if you do that arbitrarily, very likely your wave function is not the ground state of any local Hamiltonian. So that is illegal or not realizable. Here I just say that this kind of string liquid is realizable. There is a local Hamiltonian which have this string liquid as a ground state. So it's okay. It's a real possible ground state. That's another point we should make. Yes.
Knowing that this model is exactly integrable.
Yeah.
Knowing that this integrable.
Yeah.
This is integrable. Is there any interpretation in terms of this string fluctuation picture?
Yes. Actually, you can see in the fluctuation, I already say that this kind of reconnection rule with the plus sign is consistent. You can make a string fluctuation and go in a loop and go back to original configuration. You got a sign plus 1 sign. So there's no actual sign. So this property is related to this exact solubility. So if if the Hamiltonian, this will give you a string connection, when you go around the loop, they don't come back, then the ground state is frustrated, then it's not soluble. Yeah.
But that doesn't look very intuitive that the converse is true, right? The non-changing the sign non-changing, to me, doesn't imply any integrability, of course. But
yeah, I don't say integrability. It has several meanings. And here just say that, this kind of fluctuation, like taking 1 step in some direction. You can do this kind of string crossing in different places and take many steps. When you're taking many steps, sometimes you find that after many steps, you'll go back to original string configuration. And hopefully accumulated the sign for this loop is 1. So that means that the wave function is self-consistent. And this self-consistency imply that this kind of a Hamiltonian term implying implementing this self-consistent dancing rule to actually stabilize the code. They commuting projectors. Yeah. However, if you're going along the loop, you get actual sign like actual flux. And this kind of dancing rule means those Hamiltonian terms do not commute. It's not commuting projector. And if the commuting projector is soluble, and yeah, you can say that also integrable, but integrable have another meaning from beta ansatz level. It's very different from the beta ansatz integrability. It's just this Hamiltonian is a sum of commuting terms. Yeah.
I have a question about the, so you said some of the string models can generalize to 3D and some are not.
Yeah.
And then about the toric code, you said like fermions can exist in 2D and 3D.
Yes.
But if I generalize the string model you wrote down to 3D, then don't I just have like electric charge and the flux line, but not fermion?
Yeah, for this particular one, no, you don't have fermion.
Yeah, so
and
I was curious, like why you mentioned the fermion there.
Yeah. Oh yeah, that's maybe a mistake. So actually, there's for this string net a string model is also this a Topological model. The 3D generation, the end of string is boson, not fermion. But there's another version. End string can be fermion, but that's more non-trivial. Yes.
I see. Thank you.
And so at the moment, you know, we just have some kind of a Hamiltonian model realizing string liquid. It did not argue or did not show this string liquid is topological order have Lagrange entanglement. We don't show that. But here is a way to show that, because this fourth sector for string liquid wave function, there's no string and the string can flush arbitrarily, imply that both Q and F are equal to 1 on those of all the 4 states. So all the 4 states are really ground states. They have same ground energy. So this really try to show that this Topological model have a 4 degenerate ground state on the torus. So that's a sign. Yeah, maybe we have a ground degeneracy. Maybe it is a topological order. Yeah. But then actually there's another thing is that there's another sign topological order which probably is more experimentally probable. Because the measure degenerate ground state, you know, I don't know what to say. The physicist right mind should not do this because it's not measurable. At least condensed matter physics should not do this. But actually, if you do computer, it's okay. Yeah, you can put your system on the torus in a computer, then you can still do that. But however, if you study excitation in the Topological model, there's some interesting feature. Because as I mentioned that the ground state means that this F and Q equal to 1, that gives us ground state. But we know F and Q have an eigenvalue plus minus 1. If you're changing the wave function to make a 1Q equal to minus 1, then you increase energy by 2U. If you make a 1F from plus 1 to minus 1, you increase energy by 2G. So you can see that that's excitation. You can have a quasi-party excitation. That's a F and Q may flip sign. The energy gap for the excitation will be either 2U or 2G. And when you measure the heat capacity, you will see this activation gap. You'll see the smaller one, either 2U, 2G. When it's smaller, you'll see the activation gap. But then, very interestingly, there's a reason, for some reason, we can never create a single F flip, a single Q flip. By heating the system with a neutron beam, for example. When you heat the system with neutron beam, you interact with the spin, and then you may create excitation. But for some reason, you can never create a single excitation. You always create a 2. So therefore, the energy gap in the Hamiltonian spectrum actually is not 2G or 2U. It's double that. It's 4U, 4G. So it's something quite interesting. Okay.
I'm sorry, is G coupling or the G?
Yeah, G just this coefficient, the G and the U. So Hamiltonian have these two terms. Yeah. And so therefore, you can, in principle, you can do the neutron scattering, hit the sample with a neutron and measure the neutron gap. Then you can compute, you can measure the heat capacity and to measure this excitation gap. If the neutron gap and the thermal gap do not agree and differ by 2, I think that's the simplest way to see, yeah, you have a fractalization. Yeah, that's a sign of topological order. So now I'll explain why we can never create a single excitation, single F or Q flip. The reason is that this is the excitation. And the reason is following. To flip F, let me see. Okay, like to flip a Q, we need a string operator. That's the key. So let's describe that. So the string operator is like this. Yes, here's the sigma x, the x also sigma x, it's the same thing. So we just apply x along this red line. Then you'll see that originally there's no string, then flipping that we add the string. Then you can see on this vertex, there's only one red line, means Q is flipped. On this end, again, one red line, Q is flipped. But in the middle of the string, the Q is not flipped. So there's no energy cost in the middle of the string. So when you apply this string operator, you always create a 2 excitation. And although string operator is extended operator, but in the middle, there's no energy cost. And so the string operator not creating a string excitation, creating 2-point excitation. This is something special about Topological model. You may say, although I don't want to create a 2 excitation, let's create a 1 by applying a single x. If you had a single sigma x, you still create a 2 Q flip, but they are very close, a dipole. So somehow you can never create a single Q flip because string always have 2 ends. The same thing for the F flip, where we have a string operator on the dual lattice. So this the center of a hexagon from a dual lattice. Okay, and then you can see that on the end of the string, one of the spin is a flip, but this is sigma z. Okay, and so you can see this. Okay, the string operator at the end do not commute with F because F is a sigma x product sigma x around this loop, and this string have only single sigma z on this link. So there's single sigma z, the anti-commute. So therefore, this kind of sigma z string flip this F operator. So therefore, this that's flip F that's create another particle. They call M particle, and this end for this at the vertex they call E particle. Yeah. And then you can imagine we can put the 2 strings together to form bound state of M and E. So it's here. So we have this E string. Then we draw a framing of E string. Framing means that we displace string a little bit in some arbitrary direction, or the fixed arbitrary direction. Then there's a framing of this red string is using this blue line. Can be viewed as a string on dual lattice. Actually, there's a framing cut through these 2 legs. So that means on these 2 legs, we add a M string. So sigma z. And that's basically called the epsilon string, or maybe I should call F string later. This is F string. So this is a combination. So all those things can create excitations in this Topological model. And we see that they all create in pairs. And so this topologic, this excitation which cannot be created alone is called topologic excitation. And existing topological excitation also sign the topological order. Okay. Oh. So obviously, the product of these 2 string operator gave you the 3rd string operator. So almost like a fusion rule. If you a bound state of E particle, that's end of E string, and M particle, which is end M string, the bound state, these 2 particles gave you this epsilon particle, that's the end of this epsilon string. Okay. So formally, you can write some kind of fusion rule. This E and M give you epsilon, E and E give you trivial, actually. The two string together, you get no string. So there's some fusion rule, some fusion algebra. So you can still see the sign for fusion category here. But using this operator, actually, you can rigorously show that the ground state degeneracy is robust against the perturbation in some degree. Okay. So while you have a four-fold degeneracy, there's an algebraic way to see there's a four-fold degeneracy on the torus. That is the following. Actually, if this string not open from a closed string or loops, the E string loop, actually E string loop commute with Hamiltonian. Yeah, it's really because I just explained here that so let's consider Q operator. Q is a product sigma z. Then for every Q operator, we have a sigma z on this three side. But this E string is a sigma x on this red line. You can see this Q operator and the E string always have a two overlap. Each overlap, sigma z, sigma x give you minus sign when they commute, and two overlap give you plus sign. So they really commute. So similarly for the other string. And so it just commute. Okay. And so therefore, so this kind of like some kind of symmetry. Yeah. And then we can consider a long string, a loop of E string, which go around the torus in one direction, and M string go around torus in the other direction. In this configuration, very interesting. This E string and M string have only one intersection. Remember, if both strings are contractible, then either they have no intersection or they have two intersections. There's no way to have one intersection. But when both strings have this non-contractible topology, you can have situation one intersection. It's very special. Then that means that these two string operator anti-commute. But these two strings are both commute with Hamiltonian. So therefore, Hamiltonian commute with the two operator. And these two operators anti-commute. So therefore, eigenstate of Hamiltonian must from repetition of two anti-commuting operator, which is some kind of Heisenberg algebra, which have only one reducible rotation, which is two-dimensional. So ground state degeneracy must be two-dimensional at least. And we have another set of algebra, which is the M is horizontal, E is vertical. Then the same story. So actually, the two sets of operator commute with Hamiltonian. These two sets do not commute among themselves. That's how we get the four-fold degeneracy. So this kind of algebraic way to see that. Yes.
In defining the fermion, you mentioned that the framing is important. Like,
yeah,
can I always put the consistent framing, whatever the manifold I'm putting the theory on? Like torus, I think I don't have a problem, but maybe like Klein bottle.
Oh. Okay. Yeah. Okay. Yeah. You asked a very interesting question, and but I need to phrase that differently. So the background of the question is following. There's a standard understanding that is for theory with fermions, the theory is consistent only on some kind of spin manifold. Yeah. And if a fermion, if a manifold, space-time manifold now spin is inconsistent. Okay. And then but when you have a bosonic system can define any manifold, space-time manifold. And then, but then you may have an issue that you have a bosonic topology that have emergent fermion. Then, but you know your original system can be defined any space-time manifold. But when you have emergent fermion, suddenly you say the spin manifold is a non-spin manifold is illegal. You know what that means? I have understanding of this from Parsonic point of view. That means when you have emergent fermion, then the partition function of this kind of system on non-spin manifold equal to 0. So that means equal to 0 really means that's very formal. But physics really means that on the non-spin manifold, the system must contain a fermion word line or something like that. It's very much like in the spin 1/2 system. When you have spin liquid of spin 1/2, on the odd by odd lattice, you must have a single unpaired spin. So this is kind of similar. So there's a non-spin manifold in space-time. It's kind of like odd by odd lattice. You must have something, some fermion somewhere, you know, to that is so that how this spin manifold requirement emerge from this system.
Yeah, that's very interesting. Thank you. Yeah.
Okay. However, this algebraic argument allows us to show that the ground state degeneracy remain there even when we add the perturbation. So let's imagine we add some perturbation here. Then we can choose our string do not come close to the perturbation. Then it still commute with a Hamiltonian in the unperturbed region. And so the argument still works. So as long as your perturbation kind of in the local region, they don't cut, you have room to draw a string without overlap with perturbation, you have exact degeneracy. So it's kind of interesting. But certainly when you have perturbation which is wrapped around the system, you may have some trouble. But at least here is a very interesting point. Some compact localized perturbation just cannot lift degeneracy for this kind of very special symmetry. And this very special symmetry generated by those loop operators is called one symmetry. So it's higher symmetry. And this is I think in this paper, this kind of thing was studied, but they call this a gauge-like symmetry. And in the second paper, and there's a very extensive discussion of this type of thing, and also compare that to the ordinary global symmetry. So review a lot of similarity in physics. So after the second paper, this field of higher symmetry just take off. So everybody studied that. Yeah. And so I emphasize that in order to have this one symmetry, we should have this kind of commutation relation for arbitrary closed loops. So it's not like ordinary symmetry. You have one operator commutes Hamiltonian, then you have symmetry. Here, that's we have all kind of loop operators. They all commute to Hamiltonian. Then that's we say we have this so-called one symmetry. And so actually the main point of the first paper is that you try to propose that the topological order actually is coming from this kind of symmetry, so coming from this gauge-like symmetry. But here I want to emphasize that although Topological model have this symmetry, this one symmetry, and we can explain the degeneracy using this algebra using one symmetry. But the trouble is that even after we break this one symmetry, the topology is still there. So it's kind of tricky, you know. On one hand, you know, when you have one symmetry, you can get topological order. But even when you break it, you still get topological order. So the reason and the course became a little tricky. Yeah. And so let's explore this direction a little bit more. So actually, this topological ground state degeneracy can be viewed as a spontaneous higher symmetry breaking. Yeah. And so basically that's in line of this first paper. We say that we have a Hamiltonian with some higher symmetry, and if this higher symmetry is spontaneously broken, then you get the degenerate ground states. Yeah. And the reason for that is
Question.
Yeah.
This previous slide.
Yeah.
So I understand you I mean in the topological ordered state you create this new symmetry called one symmetry.
Yes.
And the last line you said you can even break this one symmetry and this still ground state remain exact?
Yeah, exact remain degenerate. Not exact, but have exponential splitting. Exponentially small splitting, no longer exact.
My simple question is how do you break, or what's the meaning of break this one?
You just like breaking ordinary symmetry, just add some perturbation in the Hamiltonian.
You said the perturbation can be confined in the.
Yeah, if perturbation confined, you can draw a loop, avoid perturbation, so that symmetry is still exact. But somehow, but you can add a perturbation which kind of fill the system. Then there's a no loop can avoid, no string which can avoid perturbation. Then you break them completely.
You destroy some loop. That's the meaning of breaking.
Yeah, that's right. You can add a perturbation of impurity which break all the loops.
All the loop.
Yeah, you break all the loop. You can see if you only add a perturbation in the local region, then the loop which do not touch this region, then that loop is not affected.
But if you destroy some part of loops, then still you have one symmetry. Am I right?
No, I don't want to say that. What I try to say, let me answer it another way. You can add a partition on every site. Then in that case, all the loop is destroyed. Yeah, not disappeared. I mean, this relation is broken for all the loops. Yeah, you can add a perturbation to the Hamiltonian, so that none of the loop commute with Hamiltonian. Yeah.
But then you claim even in that case, still ground state degeneracy.
You still have ground state degeneracy, but not exact. But you have exponentially small splitting.
So that any configuration which has any loop is not anymore ground state.
No, not ground state. Yeah, it's became more complicated.
Right.
Yeah, the model is not solvable.
Okay.
But however, imagine you can put this model in the computer, diagonalize it. This non-solid model still give you almost exact degenerate ground state. It's a kind of exponential degeneracy. It's on a small splitting.
So that in the thermodynamic limit would become
exactly. Yeah. Yeah, that's a claim.
And it's exponential.
Exponentially, not in algebraic. It's really exponential. Yeah. Yeah, this is so actually this is a kind of a surprise from topological order. The Hamiltonian have no symmetry, but in large system sites, you have a exponentially close degeneracy. That's so why that's possible? You know, it's kind of strange. And here, yeah, we didn't really explain that, but I believe we show something which make it more plausible. Yeah. Yeah, please.
Yeah, so one common way to understand this topological order state is to use Parton description with gauge. But the last line of the previous slide means that if I do not have gauge symmetry, still topological orders are well defined.
Okay, yeah. There are several issues here. Very interesting question. And when you have a lattice gauge theory, for example, a lattice Z2 gauge theory, then the ground state are degenerate. Okay. And then this kind of degenerate ground state for the lattice Z2 gauge theory actually is coming from topological order. That means if you break the gauge symmetry at the lattice level for the lattice gauge theory, you still have same topological, you still have a same degeneracy.
Yes.
And but this degeneracy means that low energy effective theory is a gauge theory. So that means in a lattice gauge theory, if you break the gauge symmetry at the lattice level, you still have a same effective gauge theory at the low energy. So the emergent gauge symmetry at the low energy is a topologically robust. You can break the gauge symmetry at the lattice level. So a little bit weird. That is the lattice model without gauge symmetry can give rise to effective theory with a gauge symmetry. So the gauge symmetry can be emergent. So that's another way to say the topological. Actually, emergent gauge symmetry is another way to say, yeah, we have a topological order. Yeah. And so, but the point of view is that the lattice gauge theory don't need to have a gauge symmetry. We don't need a lattice gauge theory in some sense.
Sure.
Arbitrary lattice model can have emergent gauge theory, can describe low energy effective theory with gauge field. We don't need a lattice gauge symmetry to do that. Yeah. That's a very good question. So whether topological order is some kind of low energy phenomenon. So what is the low energy effect theory for the system have a topological order? And for the Z2 string liquid we talk about, the answer is yes. The low energy effective theory is the lattice gauge theory. It's a gauge theory, not lattice. It's a gauge theory, Z2 gauge theory. But however, there are topological order whose low energy effect is not gauge theory. It's not even diagram Witten theory. Can be something more strange. And so actually can be something we don't even have a formulation. Yeah. And here I want to say that, so when you have a symmetry, what do you mean by spontaneously broken of that symmetry? It really means that we have a one ground state. We have a ground state. Okay, and then we have a one ground state. Then when you do symmetry transformation, this symmetry transformation can map one ground state to another ground state, a different ground state. And that's it. That's a very simple way to understand what the symmetry breaking really means. Okay. And therefore for the higher symmetry, this one symmetry, one form symmetry, is same thing. Yeah, this the ground state, the symmetry transformation, this loop, but the loop wrap on the whole system can map one ground state to another ground state. But there's one subtlety, that is we have to allow space to have some topology. Because if space have a spherical topology, the ground state is unique. There's no degeneracy. So we don't have such a feature that one symmetry is a map, one ground state is a map to another ground state by symmetry transformation. But however, when the space is a torus, then we have non-trivial loops. Then suddenly we have some kind of non-trivial transformation mapping ground state to another ground state. So this is this kind of new feature. The space topology is important to see this spontaneous symmetry breaking of a higher symmetry. That's just a remark. So indeed, if you do have this one symmetry, the topological order can be viewed as a spontaneous breaking of one symmetry. But if you don't have one symmetry, so now you can say that if you don't have one symmetry at the largest level, then as you go down low energy, there's an emergent one symmetry at the middle energy scale. When you go down even lower energy, this emergent one symmetry is spontaneously broken. And so you can understand the topological order this way. Okay. Then there's a similar question, whether every topological order can be viewed as a broken of some kind of one symmetry or two symmetry or whatever. Actually, one symmetry, two symmetry are described by this one group type thing. No, one symmetry are described by two group, two symmetry are described by three group. Actually, this shift of a level, and so then this spontaneous breaking of one symmetry or two symmetry would give you this higher gauge theory. Is a two gauge theory, three gauge theory, and then you may say, well, maybe this higher gauge theory describes all the topological order. No, I think topological also richer than that. There are topological order which do not correspond to any higher gauge theory. So actually, that's why I try to say that the tensor category theory is useful, because that is a most general language to cover all topological order. Certainly, you can use a one gauge theory, two gauge theory to do that, but only cover a subset of a topological order. Yeah, that's all. But still a very, very rich topological order. Yeah.
Question.
Yeah.
Physically, how you can break this one symmetry spontaneously by lowering just temperature? system should choose one of the.
No, it's not temperature changing. No, here we already call the real temperature ground state. So we tune in the parameter
okay.
like changing magnetic
But
field,
I see.
you know,
But
split
you
the system.
mentioned at intermediate energy scale.
Intermediate energy scale really means that
But besides that question, my original question is how you can break this one symmetry spontaneously in.
yeah, it's the same thing as making long-range entanglement. Yeah, here. The sum over subset of spin configuration actually give you a long-range entanglement. But long-range entanglement means you're spontaneously breaking certain, maybe one symmetry or two symmetry. But this is very indirect, I know. So actually,
System should choose among the several degenerate ground state. Systems should choose just one unique ground state. My question is how system can
yeah,
approach.
okay, yeah. So indeed, it's a very interesting question, and so yeah, this first summing over subset spin configuration is the answer to your question, but not in the form you ask your question, because spontaneous symmetry breaking is kind of give us a picture of some other parameter, some other big non-zero. Then there's a low energy manifold of other parameter give degeneracy and those kind of picture. And so indeed we can describe thing in that language. But that really became so-called string field theory. I mean, these strings are really superstring theory. The superstring theory has string field theory. In that case, the basic object is a string. Our field theory is not a function of a point, but a function of a string configuration. And the string configuration is infinite dimensional manifold. And the field are defined on this infinite dimensional manifold. So there's a field theory on the infinite dimensional manifold. And in that language, then there's a string condensation. Actually, it is a superposition of string. It's a string condensation. And then there's a string order parameter in the string field, and then your language would work. But one need to go to this infinite dimensional field theory, like a string field theory, to formulate that idea. Actually, there's people try to doing that, and I don't know whether that is convenient or not convenient. The reason is that in the ordinary field theory, you know the local interaction, just a phi square, phi cube, those are local interaction. But in the string field, what do you mean by local interaction? You know, the two string, if the part of the two string contact, means they're close, that the interaction. So this local interaction in the string field configuration space is pretty complicated. And writing down this local interaction term in the string field theory, I don't know. It's to me, it's very challenging. So actually, it's coming back to maybe I make some comment that we really, let me put it this way, let's pretend we really hate string field theory, and then we want to find something else, not using ordinary field theory to describe a string field theory, which looks impossible, but somehow it is possible. That answer is gauge theory. Using this redundancy of a gauge field, somehow this gauge theory happens to describe string field theory. And there, the locality is much easier to do. We know what is the local term in gauge theory, how to add the local term, and it's much easier. It's actually amazing that, I don't know, can I say that? That's, we know gauge theory before we know scalar theory, you know, Maxwell theory is pretty early. But anyway, so we actually know gauge theory for a long time, but only later we have this string configuration, a string interpretation of field theory, and then we realize that this gauge theory actually is a field theory version of a string field theory. Yeah, but maybe in a condensed states or something. Yeah. So this, but indeed the intuition race is very interesting, and maybe there's some direction one can do that, but it's also kind of difficult. It's not a trivial problem. Okay. Yeah, please.
So along the same direction. So if I consider a G2 gauge theory, and then by turning on some local interaction, I can make a confinement, deconfinement phase transition.
Yes.
And then your one symmetry, spontaneous symmetry broken phase, or the symmetry breaking sounds connected to this confinement, deconfinement transition. Is it true, or can you comment on this?
Yeah, it's a difficult answer yes or no. Okay. The point is that for the confinement deconfinement transition can be viewed as a transition between topological ordered state to state with no topological order.
Right.
From that point of view, we don't even have a symmetry. There's no symmetry to start with, and we already have this transition. So therefore, from this point of view, this transition that change topological order do not need to be viewed from this some spontaneous symmetry breaking point of view. It's just a change of topological order. But however, if your Hamiltonian always have a say one symmetry when you're changing the parameters, then indeed for the Hamiltonian with the one symmetry, you can changing parameter to have a phase transition, which is changing from one symmetry breaking state to one symmetry unbroken states. And that transition is a confined deconfined transition, and also this transition which change the topological order. Okay. So in that case, the answer is yes.
Okay.
Okay. So it's very tricky. It's really about because if one symmetry is emergent, then there's an issue about the near transition. Do you still have a emergent symmetry, or you lose emergent symmetry? Yeah, this things became more complicated. Yeah.
Okay. Thank you.
Yeah, just one question about how this may apply to like some other systems. So, I mean, would you say that your past work, I mean, your classic past work on the topological degeneracy of Laughlin fractional quantum Hall states, I mean, would you say that that's one of like the earlier example of spontaneously broken one symmetry?
Oh,
I mean, algebraically, it seems
yes.
like everything fits.
Yeah. So actually, the answer is yes, but certainly at the beginning, for the quantum Hall state, they also have topological order, also have a ground degeneracy, but at the beginning, we did not view it from this one symmetry point of view. Even nowadays, I think not many people view it from that point of view, because I think indeed for the quantum Hall states, there's the emergent one symmetry at the low energy, but however, this emergent one symmetry is anomalous. It's not anomaly free one symmetry, and yeah, that's my understanding. Yeah, so it's a more general one symmetry.
Is this because of the broken timer symmetry, or?
No, because the end of string is a anion.
Right.
And this anion have a non-trivial mu statistic with itself, and that gives rise to anomaly. Yeah. So actually, the end of string, the fractional statistics at end of string imply that that string generate anomalous one symmetry. Yeah. So that's from that point of view.
Okay, thank you.
So so here I just say that we have this a string operator with end string is E type, M type. I think nowadays we call F type particle. There's some particles. And certainly the string operator is a bosonic, just a bunch of spin flip. As a total is a bosonic operator. And we know that a string operator created two topological stations. So these two topological stations, E and E together should be boson. But then that leaves some room. If E and E bound state boson, E itself maybe boson, maybe fermion. It's so how do you know statistics for single E? How to do that? Okay, and yeah, this is kind of frustrating because what is a Fermi statistics? You say, oh, if wave function anti-symmetric is Fermi statistic, but we don't have this wave function with a E as coordinate. We have wave function in terms of spins, but not in terms of this position for E. And I think that's what you learn in the college. So in the PhD, we say, oh, fermion is something corresponding to Grassmannian field. Okay. And there's no Grassmannian field, you just have a spin. So we don't know what the E is what's a fermion. So it's a kind of tricky. But the point I try to make is that this more standard definition of a Fermi statistic is a little bit formal. So it's not like experimental detection, and so it's hard to implement in some situation like this. Yeah, and so then we come up with this the algebra of a hopping operator. The string operator have creating a pair of E particle. But you can also say that this string operator is a hopping operator. It's changing E particle from one position to another position. Okay, so this open string operator is a hopping operator for the E particle. Then there's a point of view is that actually the statistics of a particle is encoded in this hopping operator. If you know the hopping operator, then you can construct their algebra. This algebra tell you what is statistics. So the idea is really this. So suppose we have a four site, this A, B, C, D. Originally, you have two particles at A and D. Then we have a hopping operator hopping from A to B. So, and then we have another hopping operator from B to C. So this black one move from A to C here. Then we have another hopping operator hops from D to B. So at the end, we get this configuration. However, these three hopping operator can be applied in different order. We apply this B to D first, and B to C second, then the white one becomes on the top. Then at last, we do A to B at last. Then you can see that we have semi-initial configuration, but the final configuration have a black and white exchange. So therefore, if these two hopping process have an opposite sign, compare their sign. If their sign difference have a minus sign, that's a fermion. If no sign difference, it's a boson. Actually, in general, there's a chirality in here. So there could be an arbitrary phase. Then you get ania. So this is the kind of using the algebra of a hopping operator, you can get statistics. And indeed, actually, because we already have a string operator, and we just apply the string operator to use the algebra. Indeed, we find for the E string operator, the end of string E is the boson. For this combined string operator, it's epsilon string operator or F string operator. From hopping algebra, there's actual minus sign. So indeed, it's the fermion. So this way is a more precise way to derive that the end of string is a boson fermion. I think the colloquium a few years ago, we're using some cartoon picture to explain that. So this is a more formal way to derive this. Okay. And yeah, so I think I will stop here, and so we'll maybe take a 5 minutes break. Yeah, and
we will meet 11:10.
Yeah,
11:10.
Okay. Let me see. I need to. Oh, this is. I need to switch my slides. Yeah, I finished this part, so I need to use another slide. Oh, yeah, this No, this one. Yeah, no, it's the next slide. Yeah. Actually, originally I'm thinking to skip the microscopic because we don't really. Yeah, mainly I will emphasize on the macroscopic one. Yeah, but then I feel that if I directly cover macroscopic, then it's very abstract. Yeah, there's no model, no labs, no content. You know, I say that suddenly there's a lot of things. No, it's not sorry. A lot of new things suddenly jump out from things from nowhere. I say, maybe I should describe this as some microscopic example. Then later we'll describe this a macroscopic thing. It all looks very strange. But when you have those examples, then it looks more reasonable. Otherwise, it's difficult.
We feel more comfortable because we have a model and
exactly. Yeah. Exactly. Yeah. So that's a part I kind of really impressed by mathematicians. They don't need a microscopic model. They can think very abstractly, and those concepts seems very natural. You know, just it's very natural to have all this structure. You know, and they feel comfortable. They can think about that, the intuition, all that. And but physicists kind of I need the model. Otherwise, you couldn't think. But sometimes the model can be constraining. So I need to, like the broader, you have a model, then try to wave your hand vigorously, try to go beyond the model. But I really do feel this may be more comfortable. Yeah. If you do so absolutely abstractly, it's just
people are more familiar with the Turing code and so on.
Yeah. So all this usually prepare. Yeah, I think this is my real thing. On later another slide, another part. You know, so all the previous 3 hours really try to prepare for this for this more abstract one. Yeah.
And then the scaffold part
will follow this. Yeah. So these are like a more macroscopic description of topological order. Then from this more macroscopic description, we try to have a holographic picture for symmetry. Then to the boundary to gapless. Yeah, that's kind of thing. Yeah. So this kind of holographic picture is not coming from nowhere. There's a lot of previous experience somehow led to this picture. But this picture is quite strange. It's different from
So yesterday I sent you the email.
I got it.
If you need more,
sure. Yeah.
Exactly.
Exactly. We'll try to figure out. We'll try to install that. We'll see what happens. Yeah. Thank you very much. Yeah. This one. No, this is open. Yeah. Okay. Yeah.
So,
yeah.
You started from some timer systems, and then you introduced and then you finally get the end of. So changing the top of the top or end of the how do you interpret in terms of the original theory of the timer?
Yeah. The timer is something like a background, like a vacuum. The timer fluctuating is kind of condensing, and then in the timer liquid there's a defect. It turns out that if compared to timer configuration, this difference of timer configuration is a string. If this string have end, this end happen to be the site with no timer. So that's like a defect in the timer. So and this so actually like in the spin, in the spin system, dimer means a spin up, spin down from a singlet. When you have unpaired spin, that means the dimer don't go there. It turns out that this unpaired spin is always like a end of this string from dimer model.
Yeah, and also I have some difficulty in visualizing the introducing of one string in one configuration. We understand what.
Yeah.
Now the RVB, which you want, right?
Yeah.
Is a summation of all those.
Exactly. Yeah.
So one string at one configuration. So you mean that?
Yeah.
It always
Yeah, it's difficult to think. Yeah, it's a little non-trivial in the sense when you have a RVB, it's not a string. It does not look like string. But there's one way to make it into a string, means that we take a particular configuration as a reference point. And then for every other dimer configuration, we compare that with our reference configuration. And this comparison gave us a string. So the difference of a two dimer configuration is described by string, by loops. So therefore, when dimer kind of fluctuate, then its comparison with the reference configuration is always string, and the string also fluctuate. So in some sense, we can view the dimer fluctuation as string fluctuation. But there's a difference that there's only certain special kind of string appear in this comparison. So it's not superposition for all the loops. So sometimes the results are different, but sometimes there's enough of a loop fluctuation, so the dimer liquid is a string liquid. And yeah, there's some difference, but the difference is more technical. Yeah. So that's why the dimer liquid usually have an emergent Z2 gauge theory, is because of that. Okay, yeah, maybe you should start. Okay. So in the last 3 hours, we discussed the spontaneous breaking and this some kind of microscopic description of a topological order, so using the entanglement or quantum information point of view or lattice model, those kind of things. And so those discussions try to build some kind of experience or some kind of examples for this more abstract and macroscopic description of topological order. And it's kind of like when we describe a superconductor, we can directly describe the zero conductivity quantization vortex without mentioning this microscopic lattice model, without mentioning the electron pairing. So there's a macroscopic theory for this superconductor. And similarly for topological order, there's a microscopic one, we can see the lattice picture, and there's a macroscopic one, which you don't see the lattice, but somehow there's some way to describe topological order. So now I'm going to present this macroscopic picture. And just like a superfluid, there's a way to describe a superfluid using microscopic picture, like a boson condensation, superposition of all boson configuration. And there's a description of superfluid using macroscopic one, that's like a zero viscosity and a quantization vortex. So similarly, there's a macroscopic characterization of topological order. Actually, this come out early because yeah, we first come up with this kind of thing. So as I mentioned, we first have this ground degeneracy, which is topological degeneracy. Okay. But however, there's a problem. Topological order actually is very rich. And the ground degeneracy, just some integers. And that looks do not have enough information to describe to distinguish all different topological orders. Indeed, that's the case. There are topological orders whose ground degeneracy are totally different, are totally the same. So that you are different topological order with the same ground degeneracy. So we need more data. So actually, one way to get more data is that introducing this so-called moduli space. So that is the space of all the local gap Hamiltonian. So that's that kind of modular space. But the modular space from condensed matter physics is too complicated, and so we do not want to talk about that. And so then we consider a continuous space manifold, n-dimensional manifold with a metric Gij. So it's not lattice model anymore. But then we pretend this Gij is some kind of lattice coupling constant. When we're changing the metric, we are changing some coupling constant of lattice. And this way, we're thinking lattice model is closer to something we know in the mathematics. And so we will do that. Certainly, why the two are related, I don't know. But this is maybe a really big question. In the lattice model, it's not the manifold, it's not the metric space. But somehow the metric space emerged from a lattice model. This is a big question for quantum gravity, how that happens. So we don't know, we didn't solve quantum gravity, so we skip that question and we pretend this lattice model corresponds to the metric in the manifold. So changing metric like changing coupling constant, just pretend that. And it seems to work, so we kind of carry on through this.
So coupling
local, yeah. And for example, you have a lattice model where there's a coupling x direction, y direction are different. Then that's like you have metric which x, y are different. So kind of like that. So that is a idea. Yeah.
Why do you assume that you have a diffeomorphism invariance? If you're coming from a lattice, then
no,
it's not there at all, right?
Not at all.
It's just a cheat, or
it's a cheat. Okay, yeah. Actually, it's not cheating, but we also cheating. We didn't derive anything. Okay, but we know the reason. We know the answer, but we cannot prove the answer. The answer is the liquid I just mentioned yesterday. When the system, when the ground state can dissolve product states, it means it shows some continuum structure, no foliation. You know, the fracton phase, like a layered quantum Hall state, have a foliation. And because of foliation structure, dissolving products into it with changing foliation, then it's something different. Okay. And the manifold is like a continuum smooth small liquid, like no foliation structure. And in the lattice level, no foliation structure is phrased as the ability to dissolve product states. I think this is crucial. Any quantum many-body states which can dissolve product state, maybe that's the origin of emergent for manifold or metric structure. So this continuum manifold is a proper model for this. That means the quantum liquid is the origin of emergent manifold. If you don't have a quantum liquid, have some other foliation or some other entanglement structure, the emergent space will be different. Actually, this becomes really interesting. What kind of entanglement you can have at the lattice level, and that's correspond to what kind of a continuum picture. Yeah, that will be a lot of fun, but we believe that these dissolving product states gave rise to this the ordinary metric manifold. But how to prove that? Certainly, yeah, we have some idea. We believe that maybe from this direction, maybe one can come up with a proof. Okay, so then we have a modular space. Okay, and then for every point in the modular space, like you have a particular Hamiltonian, then you have, suppose you have a topological order, then you have degenerate ground state subspace. So there's a vector space corresponding to degenerate subspace. It's a ground state. And so therefore, every point in the modular space, we have a vector space describing ground state subspace. Then we have vector bundle over moduli space, and that's it. So, and the modular space may have a non-trivial topology, and so this vector bundle can be non-trivial. And so that is this vector bundle on modular space is actual data. The original degeneracy is just dimension of this vector bundle. But even with the same dimension vector bundle have a different twist, like this different twist, and this, so that's actual data. Okay, so that's the general. So this really things I try to say. You know, using this entanglement, we just say, oh, there's a long entanglement, but we don't have a quantitative description. Now we try to come up with some quantitative description of the pattern entanglement. So via this vector bundle on modular space, that may classify or characterize this long-range entanglement. And so now there are some details. You know, you have vector bundles. That means when you go around the loops, this basis of this vector start to twist. You get non-abelian barrier phase, and that's unitary matrix. And this unitary matrix characterize the vector bundle, how they are twisted around. So what this unitary matrix looks like? The first I want to say that there's a diagonal U1 phase. This the overall U1 phase. This unitary matrix is UN, for example. But UN can be realized U1 times SUN. And this U1 part is a non-universal. So that is for different loops, you get different U1 phase. Okay, it's non-universal. But however, the non-abelian part, this SUN part is universal. Okay, so especially for the contractible loop, if the loop is contractible, this non-abelian part is trivial. So when you in the modular space, when you go around the contractible loop, you get only pure UN phase. There's no non-abelian part. Why? The reason is the following. You can see, suppose when you go around these loops, you get some non-abelian phase. Okay. Then you can imagine you have a time-dependent system, which has just go around this control loop over and over again. Okay. So people doing that in atomic physics a lot. You're using the laser with different frequency. But we know that when you average over these many loops, you get effective time independent Hamiltonian. Okay, coming from this time dependent perturbation. Then what happens is if this loop give you non-abelian phase, then the effective Hamiltonian coming from this time dependent perturbation would connect this non-diagonal term that split ground state degeneracy. And we already know that the ground state degeneracy is robust against any local perturbation, but for the contractile loop, this time dependency only gives you local perturbation for the effective static Hamiltonian. So there's a contradiction. So therefore, for contractile loop in a modular space is a pure UN phase. Yeah, this is very important. And what is this UN phase? So let's consider the two-dimensional space. Suppose our space is two-dimensional sigma G is some kind of genus C manifold. And then we have a small loop in the modular space, and that is S1. So the total, adding this small loop, we have a sigma G times S1. So this describe a loop in modular space, but I view this loop as a three-dimensional space with some time dependence. Then this U1 particular UN phase of the going through this control loop turns out to be there's a term which is a volume term times the energy density. We can ignore that. But this UN phase, the UN phase is a gravitational term with a coefficient. So why is that? Yeah, though there's some argument, so maybe let me not explain here. So it's a gravitational transform term. And this coefficient is called the chiral central charge.
So the omega 3 is the U1 Chern-Simon or?
No, it's a gravitational transform term. Its normalization is that the d omega 3 is a Pontryagin class. So that's a normalized in this particular way. And so this is the coefficient have 2 pi over 2 and this C became chiral central charge with this normalization. Okay. So here you can see that this chiral central charge is important quantities. Somehow it appears in this Fourier bundle on the vector bundle in modular space. Something nice. Yes.
So this, so that integral thing, do you also, does it, I guess it doesn't depend on the size of the S1.
No.
Right. But then if you, as you smoothly shrink the S1, it's not going to change. But then when you actually, even though it's contractible, when you actually contract it.
Yeah, for contract, this one indeed changes. Yeah, and because you know, when you shrink this S1, yeah, this quantity is going to change. The point is really falling. For the quantum Hall, this is really like this is the effective Lagrangian for the quantum posites. And usually for topological quantum field theory, the partition function should be topological invariance. But for topological quantum field theory with a non-zero chiral charge, they are not topological invariant. You know, for different metrics, they are different. Yeah. And only the one higher dimension one is Pontryagin class, that one is topological invariant. So there's some subtlety. So this kind of subtlety of topological quantum field theory is realized in condensed matter in this fashion. Yeah, that's my point. Okay.
Yeah.
So this structure is well known in TKFT, but in condensed matter, it's just some contractile loop in the modular space, this vector bundle, and that one is associated with this quantity. So there's a connection between condensed matter and the TKFT. Yeah. Okay. And then there's a if you go around the non-contractile loops, then we could have a non-diagonal unitary matrix. Yeah. And so this SUN part starts to appear. Okay. And we know that the pi 1 of this modular space is a mapping class group. There's some subtlety here, but let me just say that it's some kind of mapping class group. And so therefore, this U from this non-contractile loop actually is a representation of this mapping class group. It's pi 1 of modular space. And actually, it's a project representation because the total overall yuan phase is ambiguous, is non-universal. So strictly speaking, it's a project representation. So therefore, this vector bundle is characterized by the project representation of a mapping class group, and also characterized by this U1 part is a chiral central charge. So there's two data. One is a project representation of a mapping class group. Another is the U1 part is chiral central charge. These two data is the actual thing we get from this kind of consideration. The claim or maybe conjecture is that the vector bundle on this modular space completely characterizes topological order. This is still a conjecture. We don't know whether it's really true or not. And there's yeah, just a moment. So here I want to say the following. There's a weaker version of the conjecture. It means this space manifold is a torus. Yeah, that's more familiar mapping class group. And so for a while, people more optimistic. Maybe even for torus, that's enough to cover everything. But a few years ago, the people found an example. The mapping class group representation on the torus is not enough. There are topological orders, different topological orders have same mapping class group representation. And so this original version of conjecture is that we have to consider all possible space manifold, like in 2 dimensions, not only torus, genus 2 Riemann surface, and etc. So actually, we studied the genus 2 Riemann surface. We find the mapping class representation of genus 2 Riemann surface for this counterexample resolving. You know, they indeed have different mapping class representation for this counterexample. So we need to go to some more more complex states.
So what was the starting point of deriving this? The result of a partition function explicitly.
This one?
Yes. Where did you start?
Oh, this one is like adiabatic evolution. So we have this Hamiltonian with energy gap. We evolve that adiabatically, then going to the same Hamiltonian.
But I mean which model you started from?
Any model like quantum Hall state, for example, which I did not discuss. And
This
the
is,
Topological, we can do this for Topological model, but for Topological model, carrier center equal to 0, so you're supposed to get nothing. And which is true, actually, for Topological model, we don't have that. Because it's commuting projector, it cannot generate this term. For quantum Hall states, if you do that, so basically for quantum Hall state, if you do this adiabatic evolution, you get some phase factor in the partition function. But this adiabatic evolution corresponds to space-time with the sigma g times S1. That's really just what we have. And then this lattice model have emergent space-time matrix. This emergent space-time matrix from lattice model would give rise to this gravitational transformer term. So that is the kind of calculation we try to do. Yeah.
So you started from some bulk, maybe timer spin liquid system.
Yeah.
And then in terms of original variable, what is the C?
That C is something you need to compute. When you do this adiabatic evolution, you see whether there's a curve, there's a UM phase or not. If you have UM phase, that means you have a C. Otherwise, you don't have a C. But this is non-trivial because you need to get the C. You need to have this omega-3. You need to know the emerging curvature, emerging metric. Because on a lattice model, you don't have a metric. You should have emergent metric. Then you have a C.
But I guess that you explicitly introduced the metric as the couplings, local couplings.
Yeah, but,
so you have a coupling.
Yeah, that's true.
Metric there.
Yeah, yes, thank you. There are some like quantum Hall states. Quantum Hall state is not defined on the lattice, defined in the continuum space with the metric. So you can have a metric coupled to quantum Hall states. Then this one really works. But if your starting point is a lattice model, then you don't have a metric. But then there's an emergent metric. Then there's actual steps. So to check this, and but actually there's a way to do this. It's from edge states. There's thermal Hall conductance. There's other way to compute the C from condensed matter point of view. It's more convenient, not from this gravitational transformer term. Gravitational transformer term is hard. In condensed matter system, it's hard to do this way. But there's other way to compute the parasite charge.
Yeah, I trust you all the correspondence, but I was curious whether this was really derived starting from some lattice model.
So okay, very good question. Thank you. So it's so let's try to say how we come up with this. And so there's a system. Say like in the continuum, we have a metric. Then there we can really theoretically compute this gravitational transformer term, and so we get this formula. And for that system, there's edge states, and then we compute the edge states, which is a conformal field theory, and we can compute this carrier charge or thermal Hall conductance. Then we find that thermal Hall conductance really is really given by this C, and then for the lattice system, which we don't have metric, then we cannot do this. But however, for lattice system, we can still study their boundary and still compute their thermal Hall conductance. Then from thermal Hall conductance, we infer maybe C must be like this.
Yeah, I was slightly confused about this. You're starting, the system where you started from boundaryless, the genus.
Yeah, these lines have no boundary indeed.
No boundary, right?
Yes.
So no edge state, things like that.
Yeah.
Right.
Yeah, so you're completely right. So when you have a no boundary, then and from lattice model is hard. Yeah. But here I want to mention that in just a recent, there's a way just from lattice model, from some kind of entanglement structure, one can compute the C directly from lattice model. Yeah. So there's a way to that. It's highly non-trivial. Yeah. The reason non-trivial is following, really is following. This expression is an expression from geometry. There's a manifold, notion of manifold. And the lattice have no motion manifold. The ability to compute this number from lattice model directly really means that you somehow understand how manifold emerge from lattice. So that calculation would touch this issue, how the structure manifold, information manifold can come up from pure lattice calculation. And so they really involve emerging gravity. No, I don't know what to say. I don't think I prove anything. Yeah, but there's some argument, there's some example,
right,
which looks reasonable. So we think the result is general, and yeah.
Prove this was the curiosity.
Yeah, the direct calculation in this direction is very difficult because from the lattice model, you need to compute the corresponding space-time metric, and then from there to get there. And yeah, I don't know people go from that direction. And if you want to have a lattice model, one usually just direct compute there's an edge state, or compute there's some kind of commutator of some spectral entanglement thing, and from there to extract this C. But why that computation gives rise to C? Because there's some other system we do know their metric, and for that system, the same calculation find agreement, and then we think, oh, yeah, there must be, yeah.
So let me try to understand the second part, that the holonomy of the vector wonder can be. So let me suppose the G2 gauge theory. So let me consider on a torus. So let me consider two non-contractible loops. So
yeah,
here and here. So
but this non-contractible loop is not in a space non-contractible, it's in the moduli space non-contractible loop. It's a deformation of a system where this deformation from a loop, but this deformation cannot shrink to no deformation. So it's a non-contractible loop on the moduli space.
Still, I cannot have some. You mentioned about GIJ and some metric.
Yes. So it's a way of deforming metric. And so yeah, maybe let me just give some example here. You'll see. Yeah. So like we have a torus, and we can deform the metric, and so that effectively like a shape of torus changes. And then when you deform to this way, you find that these two torus, although looks like different shape, have different metric, but you can do the coordinate transformation because they're torus. So this one after coordinate transformation is really this one. These are two same things. So this from here to here is a loop. But this, because but this loop somehow you can see is non-contractible. You cannot shrink this loop to nothing. So this is this is kind of loop we are talking about. And so here I just want to say that there's relation between this topological order and topological quantum field theory. What is the topological quantum field? Topological quantum field theory means that in a space-time, closed space-time, you get a number, that's a partition function. And on the space, you get a vector space. On m-dimensional space, you get a vector space. If m-dimensional space is a boundary of a space-time, you get a particular vector in this vector space. Okay. So So from topology order point of view is that this space is a partition function, total partition function, and this vector space on the space is this degenerate ground state manifold, subspace of degenerate ground states. And here we have particular evolution, some big bang, and then evolve into this space, you end up with a particular ground state in this ground state space. So all these are related. So some question? Yeah. Okay, no. And so therefore this this topology order actually is in some way can be viewed as a topological continuum field theory. It's a kind of condensed matter realization, a UV regulation of that. Okay, so with this, let's try to consider some kind of classification topology order. Okay, so yeah. So actually, in one dimensional, so actually this formula for mapping class group, for the on the torus, n-dimensional torus, is SLNV. Okay, n is the dimension of the torus, and if for n equal to 1, we get it's one-dimensional, the mapping class is trivial, and so therefore and also there's no gravitational term. So actually, there's no in 1+ dimension. There's no topology order. That's it. If this conjecture works, so there's no topology order. And but however, if you search in literature, there's a lot of discussion of 1+1 dimensional TKFT. So there's a non-trivial 1+1 dimensional TKFT. Then you say, oh, well, what do you mean? Here say topology order and TKFT related, and there's no topology in one dimension, but there's non-trivial TKFT. I think this TKFT is studied as a mathematical object, and from physical point of view, this 1+ dimensional TKFT is unstable. They have a degenerate ground state on the circle, and this degenerate ground state is not topologically protected. It can be split by perturbation. But the mathematicians do not study this perturbation. And what they studied, exists a fine-tuned physical system realizing this 1+1 TKFT, and that is true. So there's a fine-tuning. And if you add the stability condition, you say your TKFT should be stable against arbitrary perturbation, then all this 1+1 TKFT is unstable, and so that's why it's like a fine-tuned thing. So that's why there's a little bit difference. Okay, and so for the for two-dimensional topology order and maybe three-dimensional space-time TKFT. And as mentioned that we have ground degeneracy, we have this vector bundle, and there's a local U1 curvature, which is give us this chiral central charge. And for in two-dimensional torus, and this mapping collapse with SL2Z, which are generated by this Dane twist. Now this 90-degree rotation. So that's generate this SL2Z. So therefore, this non-abelian part is a representation of SL2D. And somehow, yeah, this part is a kind of a tricky. And so somehow these two representation combine into some kind of project representation. There's the central charge somehow appear here. So usually for the SL2D representation, ST cube should equal to C and C squared to 1. So this, if C equal to 0, that is a representation. If C not equal to 0, actually we have some kind of twisted, some kind of project representation. So this is so at the end, so this is called modular data. ST and C is modular data, and whether can this characterize all topology order is the question. And the answer is no, as I mentioned. Yeah, and there's a counterexamples. But for the genus 2, if you do the same thing, we can resolve counting example. Then there's question, if you include genus 2, whether it's complete or not. Maybe not. Then we should include genus 3 and genus 4, etc. But actually, there's people study this kind of thing. There's a reason to believe it would stop somewhere, maybe genus 2, genus 3, because higher genus can be decomposed into a lower genus. Genus 1 is too much. Well, including genus 2, maybe at the most genus 3, seems that's general enough to cover all the cases. So I don't know. Yeah, this is the open question, and there's a hope. Maybe genus 2, genus 3 is enough to cover everything. Yes.
For a given QFT, let me suppose to have some metric G mu nu.
Yeah.
So then how can I know the moduli space structure for given QFT G mu nu? So how can I know the genus structure, for example? Usually
it's a mapping class group, because you can see here because this we only care about the representation of a pi 1 of moduli space. For the pi 1 moduli space, it really corresponds to mapping class group. And so therefore, we don't need to know detailed information on moduli space. As long as we know it's a mapping class group, then we can carry on, we can do this kind of thing. And then now here is a proposal, really the conjecture is that the mapping class group is for the torus is really SL to the N. This is the result for the manifold. It's not the result for lattice model. And so we jump, so we say lattice model and the manifold may be similar. So we're using the result from manifold to conjecture that the pi 1 of the mapping, pi 1 of a lattice model moduli space is also SLZN. SLNZ, yeah.
Does it mean you just put, I still don't, so given lattice model, so does it mean you put the lattice model on torus? Then
yes, yeah, we put lattice model on torus. The lattice model have a periodic boundary condition in both directions. But however, coupling constant can be pretty arbitrary.
Yes.
So that's play a role like metric. Like in lattice model, you can hop in X direction, Y direction, or X plus Y direction, you know. This kind of hopping amplitude give you some sense of a local metric, and that's play a role of metric.
But you just put that for the metric has some torus structure.
Yeah, the lattice already have a periodical boundary condition, so your topologically is a torus. The metric is something more detailed about the shape of the torus. Then that you can tune, you can adjust. That's give you a moduli space. Yeah. Okay. So so here is really the main thing. So now we have this quantitative description of topological order in some sense. Let's stick with STC. It's easier. Even though it's incomplete, let's just carry on with this data. It's pretty complete actually. We don't miss too much. So let's carry on. So the issue is the following. For every topological order, we can obtain STC. We can obtain this data. Okay. So now let's think about suppose we have some kind of, we just give data STC which satisfy this condition, you know. So STC satisfy this condition, and we can find many triplet have satisfy this condition. Then the question is that are they describe a topological order for every possible choice of triplet? The answer is no. That's the condition we have is too weak. So so actually we need to find more conditions to restrict the allowed STC. We hope we find enough condition so the STC satisfy those conditions always correspond to a topological order. But maybe not one, maybe several, because STC is not full data, it's a partial data, maybe several. So the key question is that how to find more conditions. To find more conditions. Yeah, that is the question. And to really come to addressing this question, and one need to have become something more sophisticated. Okay, one need to go to the study topological excitation. Actually, study topological excitation is like a study space with punctures, you know. And so, for example, for the torus can be viewed as a sphere with a handle. You can make handle very, very thin and remove that, you get a sphere with two punctures. Then hopefully this mapping class group representation of a torus became this braiding of punctures. So yeah, it's not unreasonable to see there may be some connection like that. So therefore we can study the sphere with the punctures. And then there's also a vector bundle on the moduli space of sphere with the punctures, and that vector bundle may characterize this. And actually, the mapping class group for sphere with a puncture is a braid group. So indeed, it's true that this the braiding statistics, this phase from the braiding is characterized as a vector bundle on the sphere with the punctures. And so therefore, so now you can see that there are two ways to study topological. Either use a vector bundle on space without puncture, but the space have all kind of topology. That's one direction. Another direction is that we assume space have simple topology, just a sphere, but with adding a lot of punctures. Then the mapping class group of that is a braid group. Then the representation of braid group is also vector bundle. Then that may also describe it. And now you think maybe we should study space with all kind of topology, with all kind of puncture, and that vector bundle surely should describe everything. So now you can see that we are making some conjecture here that we don't want to do that general thing. We either want to study the simple space with many punctures or complicated space with no punctures. In these two extremes, maybe that's enough information to characterize topological order. So that's the kind of thing we do. And so now we'll switch gear a little bit. Now we want to concentrate this picture. The simple space with the punctures, what they're braiding and things like that. And this actually led to the modular tensor category picture. So actually this vector bundle on this modular space of punctures correspond to modular tensor category. Yeah, so basically that is a statement. So this modular tensor category have this kind of winding history. You know, there's a study of TKFT and this relation to the conformal field theory that witnessed this Jones Cornelian paper. And then studying TKFT, conformal field CFT, and they find there's a modular tensor category inside the CFT. So from here you can see there's a connection from this TKFT to modular tensor category. That's maybe that's the earliest indication there's such a connection. And so today we try to using this excitation and their braiding, their fusion, try to directly see the modular tensor category coming from this. Actually, in the early days, there's already one indication. This excitation and quantity density are related. It's really this picture. You can see, suppose we have an XY is a space. We can create a pair of onions and tunnel through the space, go around the loop. So that's like an instant time, which change this degenerate ground state to another set degenerate ground state, some kind of unitary operator doing that. Then we can also do another pair of onion, but in the Y direction. And then do the X direction, but in the opposite way, and the Y direction the opposite way. So this kind of four tunneling loop of onions can be deformed into these two linked loop of onion. And this kind of linked loop is like a space-time picture of a moving one onion go around another onion. And we get mutual statistics from there. And so that means that these four operator form algebra. They do not commute. the commutation relation give you this actual phase factor, which is mutual statistics. And this phase factor is really just actually, I should say mutual statistics. This one is mutual statistics, not a self statistics. So there's 2 pi p over q. And the denominator q I think ground state is the multiple of this the denominator q. So from here is a really very strong indication that this modular tensor category and this ground state inertia have very close relation. But how to get this very systematic relation? How to see them more systematically? So this is now from here we start to really introduce this modular tensor category, but from kind of physics point of view. Okay.
Before we proceed, so we started from the capital system.
Yeah.
And then you introduced some topological excitation.
Yes.
Which actually is not a ground state, right?
Yes.
So what is the energy scale of this topological excitation compared with the original cap?
Can be same order. Yeah.
Can be same order.
Yeah. So the topological excitation can be of order cutoff energy scale. Don't have to be very small. Yeah. And but however, by creating these loops, you need to generate a mapping between ground state. This is like instant time, which is generate the mapping between ground state.
But you request that those excitations should be, I guess, within this gap. Original
no,
gap.
One don't.
You don't.
One don't. Yeah. And actually, the reason we don't actually is really will appear here. I hope this answers your question. You know, what do you mean by topological excitation? Because when your topological excitation have very high energy, it will decay into many other things. Then it's not well defined. Yeah, there's an issue. What's topological excitation?
Why they are related?
Ground state, I mean, the
exactly.
excitation.
Yeah. So
like
that later, this really try to define this notion very carefully, and you'll see this structure. Yeah, really is really here, and you define this topological very carefully. You'll see the modular tensor category, and you'll see the ground state inertia and all that associated property. It's all coming from there. It's just like in the beginning, we define gap system very carefully. It's the sequence of a system. Then you finally get a lot of things from this very careful definition. Here we try to do the same thing, try to very carefully define this point-like excitation. And without the interference of this, they decay into some other things. That makes things very complicated. Yeah. So the idea is that so we have a Hamiltonian which have an energy gap like this spectrum. Okay. The idea is that we add the traps. Okay, we add the traps. The trap just like we modify the Hamiltonian near this point or near the loops, we add the traps. When you're adding traps, then we have a spectrum of this new modified Hamiltonian. We assume the modified Hamiltonian also have energy gap, also have this kind of spectrum. Then, but however, now the new ground state subspace will be new wave function. We call this new wave function is a wave function for excitation. So basically, ground state of a Hamiltonian with a trap is a wave function for excitation. Yeah. So basically, this is really definition for gapped system. The excitation is something trappable. Something can be trapped. So this is a crucial step. That's the definition of a point-like or string-like excitation. Something can be trapped. Okay. Then we start from there. From here, we can derive everything. Yes.
So for like Lofton wave functions, would you say a quasi-hole?
Yeah.
Is precisely this?
It's precisely that. Yeah. You can modify the trap. Okay. Actually, so that's something I'm not on the slide. Let me just go on. So in Lofton wave function, we know there's a fractional charge particle. Suppose you add only one trap only 1/3 the charge. Then suddenly find something really strange. You have a sphere within the charge. Then with the one trap have only 1/3 charge. What's going on? What happens when you add one trap? You don't have this kind of spectrum. It's complex because there are two other 1/3 particles moving around on sphere. Without localization, they get continuum. So to get energy gap, you have to have 3 traps simultaneously. And so therefore, to have this spectrum, you require you have to have 3 traps. So this is implicit. So when I say we require this spectrum, we already say the number of traps should set by certain condition to use this way. Yeah, that's very important subtlety. Okay. Then and here there's another subtlety is that for point-like excitation we have no problem, but for string excitation, what the trap Hamiltonian should be localized near string, but what along string it should be local or not local. Yeah, this is basically the open question. Yeah, we don't know what is the proper definition. Whether local one is more proper or non-local one is more proper. And I think I disagree with my collaborators on this point. I myself prefer non-local one. Yeah, in our paper, sometimes we say local, sometimes we non-local, so we cover both sides. And I think in this paper, we try to say maybe non-local one. I think non-local one is a possibility should be considered seriously. But however, the theory for non-local one is not developed. So I don't know, yeah, I don't know what is the proper thing. Anyway, so this is another subtlety is kind of open question. Okay, so now let's say, now we have something can be trapped, but the thing trapped at sigma Ca1 may be trivial. So how do we know this particular trap for trivial excitation? So that's really about the type of excitation. What do you mean by trivial? What's the non-trivial? And the trivial really means that suppose we can have a unitary operator which only use act on the site near Ca1, some local unitary operator. If this local unitary operator can rotate the wave function to the wave function with 0 trap. So you can see when you don't have Ca1, that means there's no trap near Ca1. So that's another trapped Hamiltonian, another ground state. If this ground state can be rotated into the ground state without any trap at Ca1, it can rotate away. Means that the trapped excitation at Ca1 can be created or annihilated by local operator. So it can rotate away, it can be destroyed by local operator. That means trivial. And this is a very important notion. So this kind of notion gives rise to equivalence relation. If something non-trivial, suppose there's some excitation non-trivial cannot be rotated into trivial one, but two non-trivial one may be connected to each other by rotation. So let's give us a meaning of types. If two traps can be rotated into each other smoothly without closing energy gap, then we say these two traps actually define same type of excitation. You know, originally excitation are labeled by this delta H Hamiltonian. It's very non-universal, have a lot of parameters. But when you implement this equivalence relation, there's only a few types at the end. There's only a few types. And this is a so-called anion type. You know, this topological excitation type is defined this way, very carefully using traps. Yeah, we get that. Okay. So then there's comes something which took me a few years to understand. That is the simple type and the composite type. Usually in physics, we don't worry about this. And it turns out that we always consider simple type. But the mathematicians are much more careful and they have the notion of simple type and composite type. And what's the difference? The simple type means the stable type. Usually when you have a trapping some excitation, you have a ground state substrate, we usually automatically assume this ground subspace is stable, it's generic, it's not fine-tuned. But it could be fine-tuned, means if you add a little perturbation, change a little bit, they may split. So this is a new situation. And usually in physics, we think this is illegal trap. We don't think about this trap. It's too fine-tuned. But the mathematician treat this trap as a legal as a stable one. Then they call this trap is composite. It's accidental degeneracy of two simple one. So actually the extension in the mathematics have simple type we call stable one, or composite type means with accidental degeneracy. And this notion turns out to be very, very important. That is the composite excitation can be viewed as a direct sum of two simple excitation. Actually, we know this kind of notion. We just don't emphasize that because we have a fusion for two spin 1/2. It's a spin 0 and spin 1. It's not a bound state of spin 0 and spin 1. It's odd. But the odd not superposition of spin 0 and spin 1 is something. Actually, the direct sum of a Hilbert space. Yeah. That's why I'm very careful to writing plus with a circle, means a direct sum. Because when I first reading this in some mathematical book, they just have plus. Knowing quantum mechanics, I'm thinking of this plus means superposition. Then I don't understand what is meaning of this fusion rule. But it's really a direct sum. Yeah. Okay. So then finally we can define the data for modular tensor calculus with all these notion and the types. Okay. And the most important thing that when you have suppose we have two trapping two stable excitation I and J. Then if you stay very, very far away, these two traps can be viewed as a single trap. But this single trap is very special. It has two separate locations, very special single trap. So in that sense, it's a time tone. So these two traps, when you do the single trap, its time tone can represent composite excitation. So that's a fusion. So I have two single excitation I and J together. It may be the composite one, K1, K2, K3, and composite. And there can be several K1. So K1 may appear twice. K2 may appear once. So then we formally write this as a direct sum of an Nijk with a K. Nijk is a non-negative integer. If 0 means the K don't appear. If 1 means appear once. 2 means that this same K appear twice in the direct sum. Yeah. And this Nijk defines the fusion rule. So that's one of the important data in modular tensor calculus. There's a fusion rule. So you can say physically, it's just like a fusion of this trap. So there's a really complete physical understanding of this modular tensor calculus data. Okay, so this is the example of the 1/2 fusion, and the coefficient is 1/2, 1/2 to 0 is 1, 1/2, 1/2 to 1 is 1, 1/2, 1/2 to 1/2 is 0, things like that. So this kind of fusion coefficient. Okay. And then there's associativity. When we have three excisions, we can fuse the Ij first, then fuse the K, or fuse the Jk first, then fuse the I. You should get the same thing. So that means this Nijk non-negative integer satisfy this kind of distribution. Okay. So that's start with the numerical distribution of a modular tensor calculus. There's a lot of data. The data such a lot of conditions, and the solution of those conditions is one way of the modular tensor calculus. It's very concrete. In terms of the object morphism error, the point is very abstract. So try to see what it is. But this way is very concrete. So even computer can understand that. And then there's a notion of quantum dimension. And that is already here. And you can see that the T1 have an internal division of 2. So quantum dimension is 4. And we have 2 T1 the internal division is 4. So spin 0 is 1, spin 1 is 3. So 4 times 2 is 1 plus 3. So you can see that the internal division and the fusion coefficient Nijk have relation. They cannot be arbitrary. It turns out that if you know the Nijk, you know the internal degree freedom. And this so computing internal degree freedom from Nijk fusion rate is like computing quantum dimension, which is very, very important quantity every positive particle have a lot of positive numbers. The quantum dimension is the most important quantity property for the particle. That's like just internal degree freedom of this particle. What is it?
Quantum number here is if quantum number here is
The quantum dimension is 2 for square half. But when you fuse the 2 square half together, the total dimension is 4. So this 4 dimension can be used as direct sum of 1 dimension and 3 dimension. That's 0, 1, 0, and 1. So that is a way to see how quantum dimension interact with the fusion. Yeah, to have this property. So, but amazingly, so how do you compute the quantum dimension? To compute the quantum dimension is that we want to, let's consider sphere, then we have a lot of expression. It's a lot of identical ones, lot of them. And then we compute what is the dimension of the fusion space of sphere with the minus and the I. That corresponds to how many different ways those kind of I can fuse into identity. Yeah. And so it's really that this dimension of the fusion space with the minus I, when you fuse, what is the degenerate subspace with the minus I? The answer is that how many ways we have fused minus I, how many times you get a trivial space? One is a trivial equation. How many ways you get a trivial? Okay. So it's really this picture. And I fuse you can make it M1. M1 I fuse make it M2 and second. And MN fuse I to get 1. But we make many copies of 1. Now how many copies tell you what is degenerate? Once you know the degeneracy of this I particle, you take nth root of this degeneracy. Yeah, here. So this degeneracy, the degeneracy can be viewed as the nth power of the degeneracy because we want to view this total fusion space as a tensor product of individual vector space. Because that's we have many particles far apart. The total degree freedom to be tensor product of each individual vector space. So the dimension should be split like that. If each individual vector space have a dimension di, then di to the nth power should be the dimension of this space. It's turns out that di may not have the first part.
Can I ask? Okay, so is this the fusion ring concept can go beyond the conformal field theory? Or yeah, so
this discussion is not just topological. So it's a topic of a application in topological. So actually any gap space has expression, you can trap it. And once you can have the trap expression, you have fusion ring. So all this coming from this trap and expression. Yeah, you are automatic, right? So the bottom line is that in a gap space, the category theory is a natural theory to express properties of application. Yeah, and here I try to present that picture as time division using trap. Then using trap, try to operate all the data for the
So similar question is, can this fusion ring can be defined for the system where we don't have any quasi-particle?
Okay. Actually, okay. Let's answer this way. If you're using trap idea, it doesn't work. Yeah. With the gapless trap, it doesn't work. Okay. But however, as I mentioned that we have a gapless equation, you may have emergent symmetry. The emergent symmetry, I will explain later, will correspond to topological order in one higher dimension, which has energy gap of a trap. So the fusion ring live in one higher dimension. So that's what I explained here. I first explained the one higher dimension thing. And this one higher dimension topological order corresponds to emerging symmetry of a Catholic system. So actually, for every Catholic system, there is a fusion ring. But in this way, that the emerging symmetry is topological order in one higher dimension, and the fusion ring lives in one higher dimension. Yeah. So this is description of emerging symmetry. Using relation to the Catholic.
Yeah, I guess that's right, because I think that even conformal field theory doesn't have any quasi particle.
If you look very carefully, actually, model quantum gravity conformal field is actually living in one higher dimension, not living in the same dimension. Yeah, it's but history is very interesting. We go through circles and then we understand. Oh, okay. People do big research, then find very similar dynamic structure on this domain. Okay, so I will finish that after this slide. So how to compute when you fuse many and I together, how many one do you get? How to compute that? Well, we can use infusion region. This M1 tell us how many M1 do you get? Okay. Then for each M1, this M1 fused to I tell us how many M2 do you get? So total way to get M2 that gives 3I to this product. They can go on. Then at the end, you put the large distance to 1. So this is the way you get you fuse so many I together, how many 1 you get? That's something always M2. And this expression can be used as a matrix. You can define a matrix like Ni like this. The Ni matrix, the Jk is the index, is given by this. And then this expression is really the Ni to the n minus 1 power, and taking this particular component I1. Yeah, it's different from that. However, when n is very large, we don't care which element we pick, because we know that the leading contribution from the largest element. And then there's other thing don't scale. We don't care. The thing which is scale linearly is given by the largest eigenvalue. So therefore, largest eigenvalue of the matrix is our quantum number, and which is not really integer. It's an arbitrary number. So this is the most amazing thing in topological order. The quasi-particle may have a fractionalized degree freedom. Their internal degree freedom is not integer. But it makes sense because we are still thinking with n particle. This one is integer. That's physical. That's integer. But this attempt failed. If you really do this way, each I should have a non-integer dimension. This is kind of finding thing. So this is one of the most important properties of a quasi-particle. And also it's a non-abelian statistic. That is for the abelian particle, quantum dimension always is 1. For non-abelian particle, it's not 1. So experimentally, if you want to probe the non-abelian statistic, this is easy to measure. Not by grading with the unitary, non-unitary, the unitary matrix from grading, that's much harder. The measuring degree freedom is much easier. Yeah. So this is the start of our model quantum gravity theory for topological order. So I will stop here.
Thank you very much. Now, open for questions. Any questions? So you mentioned in experiment, if I try to measure the non-abelian particle, then detection of DI would be the easiest. Do you have any experimental scheme in mind to detect that?
Yeah, usually it's not interesting.
But as you,
Then another thing that you create a patient and put it on a line. So with the quantum distribution table, some kind of one-dimensional shape. And that one is our dynamics, and so along this line. If you really like putting a line, I don't know when I'm trying to reach the putting a line, what is there's still legal quantum systems.
Right.
what they're talking. Always, yeah. I don't know if experiment can really do this in a lot of times. The theory has a lot of job.
I see. Thank you. Questions? Yeah, let me. I think I still don't understand the very basic thing. So why is the mapping class group of the moduli space of the QFT can distinguish, can give some classification scheme for anyons? Is there any intuitive picture? Can I think?
What is anion? Okay, it's really.
So changing the metric in the QFT, then we can detect some topological structure of the theory, can distinguish some excitations, anyons. So how can I understand that somewhat more intuitively? So
the thing that, so here I try to say that, we spend a lot of time to explain, to argue why the quantum degeneracy is a topological feature, which corresponds to intrinsic state. And then here we just want to generalize this idea a little bit. This dimension of degenerate ground state is just dimension of a vector in the vector bundle. And if the dimension of a vector in the vector bundle is robust, then we are hoping maybe the other property vector bundle also robust. So this is the motivation to say, yeah, maybe you have more data. You not only consider the dimension vector in vector bundle, you consider the whole vector bundle. When you have a capital system, you naturally have this vector bundle. You can always define this vector bundle by changing the Hamiltonian, the other one subspace at the low case, we just have vector bundle. The important thing that why some property in the vector bundle is a universal, characterize the phase matter, intrinsic phase matter, is not clear. But we have same question, why degenerate ground state, is a universal property characterizing a phase matter. And that one is already quite non-trivial. If you believe that one, if you believe degeneracy of ground state is a property characterizing intrinsic thermodynamic phase, then it's easier to understand. Some property that bundle can do the same thing. So it's really effort to extract data, extract topological environment, which is characterized intrinsic phase from thermodynamic phase. Yeah, that's really the effort. Now, then the next slide, I try to explain a little bit why some features, not every feature that bundle corresponds to topological environment, but some feature like we could see. This U1 phase factor is not topological environment. But from there, we have you see. Then for the non-compatible move, it's a non-diagonal move is a topological environment. So here, but some argument, certain feature that from the topological environment, it's like the same move as different concept. Somehow correspond to the phase or phase amount. That this part is
Thank you.
I have a small technical question. So you mentioned the relation between S and T.
Yeah.
And what was the argument? There is some relation between the S and T.
First, this pi 1 is a group from a group. And so this holonomy is matrix U is a non-linear on pi 1. So this U from the potential of pi 1. So basically that is the motivation of this condition. Because this S and T is the generator of this modular group. And the generator of the SL2 ring has this relation S2 to ST2. And that's square of that equal to 1. And here we just add another phase factor so that this is kind of projected.
Right, but you certainly don't request this SL2G invariance, right?
No, it's not invariant. It's really it's a topological unit because this U, this non-diagonal part is topological, and so we have a go around one loop, loop one to another loop. It's just compose, and so certainly in general, this non-binary interface is not universal. Then things are messy because the Taiwan loop, there's many non-custom loops. You default loop a little bit and use the chain. But here you don't. This U is the same for all the class of the homotopy class of the loop is the same. The composition of the two loops, it just gives you a representation of Taiwan. So U is the representation of Taiwan. I don't call that invariant. It's not symmetry. It's just the composition rules are not being verified. Yeah, the non-binary just compose. When the loop compose, the non-binary loop compose.
More questions? So according to your example of how to count quantum dimension using spin 1/2, it's obvious when you have bound state, singly bound state of spin 1/2, then quantum dimension is 1, and that object is abelian, right? Spin singly. But
because I just mentioned the quantum dimension now is 1, it should be not abelian.
right.
You know how quantum dimension 2 is not abelian.
How can I understand?
Yeah, this is a shallow case indeed. Mathematician would call not abelian. Actually, we have a similar issue. Have a non-abelian gauge theory. Sometimes the gauge charge is not in gauge theory. This representation gauge group. And this gauge charge can be the higher dimensional representation. This dimensional representation actually is quantum dimension. So then you say in the non-abelian gauge theory, when the gauge charge is a non-abelian statistical number. Again, it's a trick. I think you are totally right. Physics would say they are both, and they have abelian statistics. But the mathematician using quantum dimension, they not. But here I do want to mention that mathematicians have a little bit of reason like how that. We have spin 1/2 when you're braiding two spin 1/2 together. You say you should have not no phase. But this is actually very tricky because when you have two spin 1/2 far away, you have the 4-dimensional degenerate space. When you braid them, how do you show there's the 4x4 matrix is trivial, especially if there's some spin orbital conflict. Even when you break it very slowly, you may still have this non-trivial phase. And so actually, if you think about that, it's highly non-trivial. It's material dependent. In the material with spin orbital coupling, you have some non-trivial phase. So then you may say, oh, maybe the material with spin orbital coupling is not abelian. Without spin orbital, it's abelian. So actually, when you have multi-component particle, but when you have particle with a non-zero quantum dimension, the braiding can be very tricky. And saying braiding is trivial is too fast. Even in condensed matter, there are situations of braiding can be non-trivial, even for spin particle. And but usually, yeah. So actually, using braiding to define statistics is kind of delicate. And
but in condensed matter, we know everyday experiment spin 1/2 particle is abelian.
Yes and no. I think when you have a spin orbital coupling, when the brain is not up, I will make
Okay, okay. If you have,
maybe this is a very interesting question. That is in a material with a strong spin opposite couple. We have gases, are moving on each other. It's who knows? Maybe this gas is not ordinary boson gas. May have different behavior. That still concerns me. Yeah.
thank you.
Are there any questions in Zoom audiences? I'm just asking. If not, thank you very much. Let's end today.